We're going to talk about rigid body dynamics for symmetric bodies. It's a rare YAM that is symmetric, but we're talking about things like this can. So to a very high degree, the moment of inertia about this is going to be different than these two, but these two will be the same, right? The moment of inertia about this because of the axisymmetry of the can. Also things that have a square cross section. So the moment of inertia is going to be the same. This is axisymmetric. And you can even have other cases of symmetry like this cube, all the axes, if you choose your principal axes to be along the faces of the body, they're all going to be equal because it's to machine precision, the same mass distribution of each of those axes. We're going to focus today on axisymmetric bodies because we know how to handle that analytically. And then later we'll deal with the general case of the YAM, the arbitrary body that has, it doesn't have to be a YAM. It could be something like this, something rectangular, but all the cross sections are different. In general, you're going to have different principal moments of inertia. So what does the motion of that even qualitatively look like? But first, we can be quantitative, calculate things for the symmetric body. So we're looking at torque-free motion of a symmetric body, where here symmetry means that two of the moments of inertia are equal. Two of the three principal moments of inertia are equal. So you could think of the solid cylinder, where if you've got a frame that's centered at the center of mass, V1, V2, V3. In this case, the moment of inertia about, let's say this direction, we'd call it I1, and this is I2, but it's equal to I1. And so we call them both IT for transverse to the axis of symmetry. In this other direction, the moment of inertia is I3, and this is not equal to IT. And in fact, this is a case of I3, because if you think of the amount of mass that's perpendicular to that axis, it's going to be less than about either B1 or B2. So this is going to be less than IT. So this is a situation called prolate. It's like tall and skinny things. This would also qualify, right? What is this, like a block, the cross section that's square. The other case would be, and either you squish this and make it into a coin or a frisbee, or just something that this is a square cross section, but it has not an infinitesimally thin direction, but it's just thinner. So this other case, the moment of inertia about this direction, still call this B3, I3, and it's going to be greater than IT. So each of these is IT. These two cases, case one is prolate, the other case is called oblate, short and squished. We ended last time with writing the Euler rotational equations of motion. I'll just repeat them here. The Euler equations of motion, when we have torque free or a free rigid body, means the moments are zero. There's no applied moments. So this is just something spinning out in space. If you're on the space station and you give this a spin, this is what it'll do. Or we say the moments are negligible. So even tossing your phone or tossing a book with negligible aerodynamics, you could say, well, the moments are close to zero. So good enough. These are the Euler rotational equations, and I will write it this way. This is in general, but we can make some specialization to this case of symmetry, and then some terms will drop out and simplify. That's always a good first step whenever you're studying a system. Look for cases where it simplifies enough to the point that you can solve it. I1 minus I2, omega 1, omega 2 equals 0. So I'm sort of following what's in pages 182 to 183, but I'm doing it differently and better. Okay, so if we specialize to this case that I1 equals I2, and that we'll call them both IT, transverse, then what happens here? Let's just write it out. So I'll write it down here. IT omega 1 dot minus IT minus I3 omega 2 omega 3 equals 0. IT omega 2 dot minus I3 minus IT. Omega 3, omega 1 equals 0. And then I3, omega 3 dot minus IT minus IT. Ooh, cool. Fancy way to write 0. Zeros mean something's going on. Well, so that one's easy. So this means immediately omega 3, just divide by I3. This means omega 3 dot equals 0. So omega 3 is a constant. So that means the third component, if we're in the body fixed frame, and this is omega, the number 3 component is always going to be staying the same. So that means the projection of the orange vector along this B3 direction, let's call that the B3 direction. That just stays constant. So I don't know what the others do, but that one stays constant. So if you want omega 3 as a function of time equals whatever omega 3 was initially. All right, what about these other two? How do I deal with them? Well, it looks like if I were to rearrange, I could write this, just flip the sign, and I'll say this is plus I3 minus IT. And so then it looks like maybe I should define something that's related to, right, I3 minus IT and then omega 3, which I now know is constant. And the same thing is here, I3 minus IT omega 3. So I'm going to define omega n, and this is equal to, I'll just divide by IT, 1 minus I3 IT omega 3. This is the opposite of what the book has. So just so you know, book uses what it calls as omega p, which is negative of what I have as omega n. We'll put that in a very hard to see blue. So then if I were to write this out, these two equations, the third one's solved once and for all. So I'm not going to get any more information out of it. What are the other two? I get omega 1 dot minus omega n, omega 2 equals 0. And then omega 2 dot plus omega n, omega 1 equals 0. And I could just take another derivative of each. So this would give me omega 1 double dot minus omega n, omega 2 dot equals 0. Oh, wait, I have omega 2 dot down here. And if I rewrite that, what does that give me? So this will give me plus omega 1, and there's an omega n squared. So I get that. And the same thing happens down here. If I take a second derivative, omega 2 double dot plus, I get omega n squared omega 2. So now I have what look like two uncoupled simple harmonic oscillators. So both look like they're going to do simple harmonic motion, sines and cosines, right? For each of them, it would be like A cosine omega n t plus B sine omega n t. And you could get A and B from initial conditions. So now I'm going to pick some initial conditions that make this nice. I'm going to assume initial conditions just to make the equations look okay, where omega 1 at time 0 is negative omega naught, and then omega 2 at time 0 is just 0. And then omega 3 at time 0 is just whatever I want to call it, omega 3. It's just a constant. It's solving for what AI and BI. Then my solution is omega 1 as a function of time is negative omega naught cosine omega n t, right? Keep what omega n is. Omega 2 t equals omega naught sine omega n t. And we could think about what's going on now. Maybe these are body fixed frame components. So what do I have? I've got those two cases, and that changes the sign of omega n. So for the prolate body, I've got I3 over IT is less than 1. So that means omega n is positive. For I3 over IT less than 1, omega n is positive. And then the opposite for I3 over IT greater than 1, omega n less than 0. So the first one is prolate, oblate. If we were to just look at what is happening in the omega 1, omega 2 space, really this is just the projection along B1 and B2. And I'm starting over here. So I've got my vector for omega starting pointing that way at time 0. If omega n is positive, moving that way. So this is omega n positive, And if omega n is negative, I'm moving that way. Either way, I'm on a circle. So this is a circle of radius omega naught. So putting it all together, I'll try to make something prolate looking. And then I've got my omega vector. The B3 component is constant. And then the tip of that vector is going to trace out a circle. It's going to trace out a circle. So at some later time, right, maybe the vector is pointing that way, sometime greater than 0. This is at time t equals 0. And it'll be tracing out basically a cone about B3. So omega vector traces out a cone about the B3 direction. That's it. It traces out a cone. We know what the period is. The period's going to be 2 pi over omega n to complete the cone. That doesn't tell us yet what the motion looks like in three-dimensional space. It just says, here's how the angular velocity vector, this is a free rigid body. There's no moments, but the angular velocity vector does change. It's moving around in the body fixed frame. So how does the motion look in an inertial frame? And I won't specify yet what inertial frame. Maybe I want to pick certain directions for my inertial frame. And in fact, I probably do. So there's going to be some direction that stands out. It'll be the angular momentum. We're asking this question and we'll get some idea of what it looks like. We can write the angular momentum. Remember what that is. So this is the only sort of distinguished point on the body about which any kind of rotation would occur is the center of mass. We've got some out in space. So angular momentum about the center of mass would be the moment of inertia matrix about the center of mass. Remember, all these are in the body fixed frame times the angular velocity, which we've now solved as a function of time. So maybe we could just throw that in there. For this system, what do we have for IC? Maybe I'll move this, use the lasso effect, which is appropriate. I'm kind of like the Ted Lasso of space vehicle dynamics. IC, the body fixed frame, would be IT, right? B1 and B2 are principal axes, so this is just going to be diagonal, and then the last one is I3. One of these three is not like the other. Okay, so then we could just write out the components of H. Because this is diagonal, it's particularly nice. We've got, here are the solutions for what omega looks like as a function of time. There's that, and then there was this one up here. So let me write it out. We get negative IT omega naught cosine omega n t. This is a vector. IT omega naught sine omega n t and omega 3. So that is the angular momentum written in the body fixed frame. And I don't know, maybe I'll just put it down here. Written in body fixed frame components. What we also know is that because there are no moments, the angular momentum vector is fixed in an inertial space. So whatever it is initially, it doesn't change. It can't change because there's no moments acting on it. So if you remember what we had, right, what's the inertial derivative of the angular momentum? It's the moment, but this is 0. So that means omega c written in the inertial frame is a constant. It's a constant vector. It's pointing in a constant direction. So that sort of suggests maybe I should use that as one of the directions for my inertial frame, just to make life a little bit easier. I'll use the unit vector in the HCN direction as one of the unit vectors for my inertial frame. HCN, it's not necessarily normalized. To normalize means to make it equal to 1. There, now it is. If you want a picture in mind of what's going on, we're just looking in the B1, B3 plane. Initially, omega pointing this way. This is omega 3, and this was omega naught. Notice I have it pointing in the negative B1 direction because that was the initial condition. Applying what direction is the angular momentum in? It's in a slightly different direction than the angular velocity because IT is not equal to I3. So there's going to be some slight, it doesn't have to be slight, it might be big. So that's the angular momentum direction. It's a constant direction. Constant in inertial space. And it's got a special property. If we take the dot product of the unit vector, take the dot product with B3, we'll get something that is equal to I3 omega 3 divided by IT squared omega naught squared plus I3 squared omega 3 squared. Maybe I'll move this over because these are two unit vectors. Whenever we have two unit vectors, we can write the cosine of the angle between them. So what's the angle between these two? Well, it's this angle, theta. Cosine of theta equals this. And notice this is a constant. So because that's constant, the angle theta is a constant. There's the B3 direction. The angle between the B3 direction and the angular momentum direction, that angle is always going to be the same. I mean, B3 might do weird things. The angular momentum doesn't change in space, but that angle between the two vectors must be constant. It's constant theta because everything over here is a constant. So that means theta is constant. And if we treat it as one of the Euler angles, it turns out we could use the 3-2-1, but it looked kind of weird. I'm going to use the 3-2-3 set of Euler angles, which I haven't spoken of before. It's one of the 12. So 3-2-3 Euler angles. And then I'll give them names. This one will kind of look like yaw, but don't call it yaw. It doesn't have a name. And then the second one is actually the same angle as this theta. And then the last one, we'll use these Euler angles to describe the motion in inertial space. We want to describe how the B frame connected to the body is changing with respect to the inertial frame. And I think I'll pick the unit vector that's pointing in the angular momentum direction as one of the unit vectors for my inertial frame. In fact, maybe I don't even need to specify what the other two are, as long as I pick that one. If you were to write this out, how do the Euler angle rates change in time? Well, from what we've talked about, and also from, you could look in Appendix B2, it's got what the kinematic differential equations, it's got those for each of the set of Euler angles. And if you remember, you write the Euler angles as a vector. It's just easier and more compact to write it that way. If you do that, then the time rate of change of the Euler angles equals this B matrix, which is different for each set of Euler angles, times omega. In this case, we have omega as a function of time. And then you could also write it as, take the inverse, and you have, okay, here's how omega changes as a function of time equals B matrix inverse times the Euler angle rates. We could use the fact that since theta is a constant, that means here we're using for theta, the matrix, psi theta phi. But we also know that theta dot equals 0. So if we were to write theta dot the vector equals, we have psi dot 0, phi dot. That'll simplify some calculations here. So what we'll end up with, well, we'll use this one. And what do we get? We'll get that omega 1 equals negative omega naught cosine omega n t. And then the right-hand side with this B inverse theta dot, just look it up, ends up being negative psi dot sine theta cosine phi. And omega 2, which we've analytically solved to be omega naught sine omega nt equals psi dot sine theta sine phi. And then omega 3 is just omega 3, and it equals phi dot plus psi dot cosine theta. So we've just sort of rewritten that. And then we could do some manipulations. I'm going to have to skip some details just so I can get through it. We could solve for, we've already got what theta dot is. We could also solve for psi dot. and phi dot. So we get that psi dot equals omega naught over sine theta. And this is the way that the angular velocity is rotating about the angular momentum direction. So if I were to draw the angular momentum direction, and here is my angular velocity, this angle is constant. So that's a theta, but this is moving around. So the omega vector, we said, was, at least in the body fixed frame, the omega vector is actually tracing a cone around the B3 direction. The omega vector in the inertial frame is tracing out a cone about the angular momentum direction. We have these two cones. We'll call this the space cone. And the one up here traces out a cone. We'll call this the body cone. We could also, it turns out, solve for phi dot. Phi dot equals 1 minus I3 over IT times omega 3. We call this the spin rate. Do we even have a name for psi dot? We do. It's actually called the precession rate. So there's a nice interpretation in terms of what these two cones do. And if I had a fancier way of cutting foam, I would have had two pieces of foam cut into cone shapes, but I don't have that. So I'll just say, here's the interpretation in terms of cones. So we'll look at two cases. First, the prolate case, the prolate body. Remember what that was. IT is greater than I3. So then what do we get for the spin rate here? Spin rate, sorry, greater than 0. Positive spin rate. So if you want, we've got a cone. I'll just draw something prolate. It's got moments of inertia that are equal, that are transverse, and then this other one, I3, on the axis of symmetry. This is actually the minimum axis. It's got the minimum magnitude of the principal moment. What do the dynamics look like in terms of these cones? I've got some nice sketches. So this gives a nice picture of what's happening. What is happening? We've chosen this direction to be this direction. The space cone is centered on the angular momentum direction. So here's our center of mass for this body. We've got the body cone, the space cone and the body cone. It's like they intersect along this omega vector, right? That's the omega vector. And the cones, it's like they're rolling without slipping about one another. So the body cone is spinning with this direction. This is phi dot greater than 0. Remember, that's the spin. It's kind of how is the body spinning? At the same time, this other motion, this is precession. And if you put the two together, right, the interpretation, the cones are rolling without slipping along the contact line of this omega vector. So what will we see? Well, depending on the different rates, you could have different things happening. You could see the motion. There's an axisymmetric prolate body. I think this is the same video I showed last time. This doesn't show the cones, but you could, this is showing omega as this blue vector that's incredibly hard to see. But you see that it's going around the H vector, which is the constant angular momentum in space. And so that's the resulting motion of the body. If you were to think of these two kind of solid cones rolling without slipping about one another. And notice here, we've got, it's got positive precession, right? Psi dot is positive and positive spin. Yay. The other case was the oblate body. IT is less than I3. So I3 is dominant. If you want, let's just take that cylinder and squish it down, but not all the way. So this is like a coin, quarter, or a frisbee. And we've got, like before, about the center of mass. There's IT in this transverse symmetric direction. And then we've got I3, which is now the major axis. There's the minimum axis. I guess we'd call it the maximum axis. The other terms would be minor and major. Maximum axis, meaning it's got the most mass transverse to it. And in that case, the orientation of the cones is different. Here we've got the space cone and the body cone are outside. For this other case, the space cone is inside the body cone. So we have the same thing in terms of what this vector kind of pointing up is. We've chosen this to be, this is an inertially fixed direction. It's the angular momentum. I guess we could, if we want, right, say, with respect to an inertial frame. It's inertially fixed. We've got this axis of symmetry, B3, and again, we've got the angular velocity. The angular velocity vector is the intersection of the two cones, but now they move differently. This is about the center of mass. We've got that the spin rate, right? This is still the body cone. The spin rate's going in another direction. The precession is still positive. If I look back at how I wrote precession, yeah, precession is just positive. It has to be, it doesn't change sign. So we still have that the precession is positive. And that resulting motion looks different. It doesn't have to actually have axisymmetry. You could have a rectangle with a cross section of a box, but it's squished. You know, boxes from Amazon, perfectly square or something. And so this is what's happening. This helps give you an idea of, okay, why is it doing this kind of tumbling thing? And this is if you started with an angular momentum that's not exactly aligned with one of the axes. If it was exactly aligned with one of the axes, this is the interpretation of a principal axis. A principal axis is a direction where if you are spinning initially exactly along that direction, it will look like pure rotation and not this kind of weird precession looking stuff. Yeah, here's pure motion. So this is this thing just spinning. There's no what looks like tumbling or anything. It's just pure rotation. In that case, I think both cones sort of shrink down to lines and they're pointing in the same direction. That's what's going on. So the general motion is going to be that kind of precession if you have something axisymmetric, which then leads to, well, then what's the general motion? If we don't have something that's axisymmetric, well, you can get other kinds of things happening. By general body, I mean, if you were to pick something randomly, it's going to have three different principal moments of inertia. So that means I1, I2, I3 are all different. The convention that we'll use is that I1 is the largest, and then I2 and I3. So we'll suppose the way that they're ordered is such that I1 is the largest, I2 is in the middle, and then we have I3. So we call this major, intermediate, minor. And so we'll have the corresponding principal axis be B1, B2, B3, so that there's no confusion. To discuss this case, we do need to mention something about the energy. We're talking about free rigid body motion still. So there's no moments acting. It's useful to consider angular momentum and energy, total energy. Now, because there's no potential energy involved, all the energy is just kinetic energy of rotation. We've already discussed angular momentum, but we haven't, I don't think I've said what the kinetic energy is for a rigid body. The formula is, we usually write it as T. We have 1/2, and you could write this as omega transpose IC omega. And if all of these are written in the body fixed frame, then we just remind ourselves of that. This looks particularly simple if we write it in principal axes. So this is the kinetic energy. It works even if you don't have a principal axis, but in a principal axis frame, what does this become? T equals, we have 1/2 I1 omega 1 squared plus 1/2 I2 omega 2 squared plus I3 1/2 I3 omega 3 squared. So it looks pretty nice, but we want to write everything in terms of angular momentum. This is the kinetic energy of rotation written in terms of omega, the angular velocity, but we could write it in terms of angular momentum. That'll be more useful for our purposes. And I'll just write it as H. It's about the center of mass. So if I write H, and I'm going to write H in the body fixed frame, just the components, because then it'd be easier to write. H1, H2, H3. T, we'll just use the formula we have that relates H and omega. So this becomes 1/2 IC inverse H dotted with H. So it's a dot product of two vectors. And if you were to write it out, it becomes, I'll write it this way, H1 squared over 2I1 plus H2 squared over 2I2 plus H3 squared over 2I3. If we divided by T, let's just divide by T, we get H1 squared over 2I1T plus H2 squared 2I2T plus H3 squared 2I3T equals 1. And now maybe you'll see something. If we were to plot what this looks like, because there's no moment acting on this, the kinetic energy is actually constant. The total kinetic energy is constant. It looks like the formula for an ellipsoid. So x squared over a squared plus y squared over b squared. If we set that equal to 1, then this looks like just an ellipse in the plane. But you add the z component, now it's an ellipsoid. And just comparing with what we have over there, we've got an ellipsoid with semi-axes of length square root 2I1t square root 2I2t square root 2I3t. If you wanted to later follow on in the book, because it also has this discussion and does it pretty well. I'm in section 4.3. So what does this mean? When a general, I don't have a general shape. Yeah, I do. Well, this one's general. If this is undergoing free rigid body, so it had some initial condition and now it's just sort of moving about its center mass, rotating. It needs to conserve energy. But if we view that in this space of H1, H2, and H3, so just think of there's the body fixed axes, but you could also call this the H1 direction, H2 direction, and H3. Depending on the relative sizes here, well, I1 is the largest. So there's going to be, this is going to describe an ellipsoid. It's an ellipsoid. We have an ellipsoid in the H1, H2, H3 space. And we'll call it the energy ellipsoid since it represents conserved energy. We're going to use conservation of energy. On the other hand, conservation of angular momentum, it means that the magnitude of H is constant. What that means in terms of this space of H1 and H2 and H3 is that we have motion on a sphere. If the magnitude of H is constant, then the magnitude of H squared is constant. So we've got H1 squared plus H2 squared plus H3 squared equals some constant. When we write it that way, it looks a lot like, right, we're writing these axes. It looks like x squared plus y squared plus z squared equals something constant. Let's call it r squared. It's the formula for a sphere with radius r. Here, r is just the magnitude of the angular momentum. Hold on, I thought you said the angular momentum is just pointing in one direction. In inertial space, yes, in inertial space. But with respect to the body fixed axes, it's just it's a constant magnitude, but it could be pointing anywhere with respect to the body fixed frame. So we have these two formulas. We've got this, an ellipsoid and a sphere. Let's call it the momentum sphere. So in terms of the same directions, H1, H2, H3, this is like instead of doing a cigar shape, I'll do a sphere. Now the motion, to satisfy both of these, the angular momentum has to be along the intersection of an ellipsoid and a sphere. It's along the intersection of the angular momentum sphere and energy ellipsoid. So there's a nice geometric picture that we can consider of what is happening here. It's just showing sort of a MATLABized sphere, the momentum sphere, and then the energy ellipsoid. So the possible trajectory, this is a possible trajectory, has to be along the intersection of the two things. So think of the vector going from there to here. That's the angular momentum in the body fixed frame. That's hard to see. And so it would be moving along there, or there's an intersection on the other side. So that's the other possible trajectory. We've already said that I1 is the major axis, I3 is the minimum axis. So we could look at some different cases now. So let's say we keep the angular momentum magnitude constant. So that means we'll keep the sphere constant, but we'll change how much energy there is, which will mean changing the size of the ellipsoid. And there's a maximum amount and a minimum amount, and then everything in between. So this is changing. So we'll have a constant sphere, but changing the size of ellipsoid. So we'll start with the minimum energy ellipsoid. So for there to be an intersection, we need that the ellipsoid is exactly inside the sphere and only intersects in 2 points. There, okay, that point and then the point back here. So that would correspond to pure rotation about the B1 direction. The minimum energy, which is the same as the maximum moment of inertia. Remember, I1 is the maximum. This is looking stable, if we had to describe it. Okay, if we make the ellipsoid slightly bigger, well, not slightly bigger, if we get it up to the point where it's as big as the intermediate, let me shrink this down so I could fit them all. So this is increasing the size of the ellipsoid. The sphere stayed the same size, but the ellipsoid is now big enough. This intersection between the sphere and the ellipsoid looks pretty weird. It intersects in this shape. If you started as close as you could get to the intermediate axis, it looks like you're not going to stay in that direction because there are arrows pointing away and it'll flip to the other side. And then what about if we increase yet again to the maximum energy? We get this sort of case. So this is the energy ellipsoid. And it only intersects in the top and then down there at the bottom. So we've got pure rotation about the B3 axis, the max energy, but minimum moment, and it also seems stable. This one, because there are those arrows pointing away, both on this side and on the other side of the sphere that we can't see, rotation about B2, the intermediate axis, appears unstable. And it is. If we were to look at on the sphere, draw all the intersections of all of the intermediate values. Here we did kind of the extreme values, but if we looked at all of the intermediate values, we would get a picture that looks like this. And this sort of summarizes it. Right? So this is just showing that we kept a constant sphere, and these are all intersections of the ellipsoid with that sphere. And so this tells us that it just sort of summarizes for different values of kinetic energy, what do we get? And we got that there's this minimum energy direction, which is stable, right? If you're a little bit off of it, then this just circulates around. The maximum is also stable because if you're a little bit off of that axis, it'll just circulate around. But if you're a little bit off of the intermediate axis, even if you're sort of starting in this direction, heading toward it, well, you will leave and go to the other side. And it doesn't matter if you're down here, you will leave. The key thing is that motion about the intermediate axis. That means the principal axis that doesn't have the maximum or the minimum, it's the one in between, because we have 3, is unstable. There's a video I could show just to end this. They do orient things differently, and they have a different terminology. But this is the constant sphere. So this is starting out with that minimum energy, and it's showing an animation of spinning about that minimum energy. Now, what about something in between? Something in between is going to do that precession type motion that we talked about. Well, it looks kind of precession-y. It's not exactly, because this isn't an axisymmetric body. And this goes on for a while. Then it goes to the intermediate energy. So here it starts off, it's rotating. This is like you flipping your phone about its intermediate axis. You could figure out what that is. And it seems to kind of be going in that direction for a while, but then it does these large flips and points in the opposite direction. This is not what you want for a spacecraft. So that's why you don't want the spacecraft to be rotating about the intermediate axis. It seems like the major axis or the minor axis might be good, but not this intermediate. If you increase again, okay, to something kind of in that range, then you get this other kind of weird wobbly precession motion. Right, and then the final case would be the maximum energy. It's got maximum energy and it looks stable. So that maybe that's good for a spacecraft. There are special cases going back to before. If I1 and I2 are equal, I could even show you what that looks like. You've got along the H1, H2 direction, it's all fixed points. So you could do pure rotation about those, but if you're anything off of that, then you'll get these, you'll be rotating around the B3 direction. And what if they're all equal? So a sphere or a cube, that maybe you could guess, you could rotate about any direction. It's all, these dots just represent their fixed points. So you can rotate about that direction freely. It's a very fragile situation though, because if you have some perfect sphere and then I breathe on it, now you've got moisture on one side and oh, you don't have symmetry anymore. But to some good approximation, you know, spheres and stuff will behave like this. So that's it.